So welcome everybody to today's talk in the computer-assisted proofs seminar. And I'm super happy to introduce Shane Kepley today. He did his PhD well, almost 3 years ago now, I think, with in Florida with Jay. And then he moved to Rutgers and he started working on some other things than just computer-assisted proofs, but okay, we're back at computer-assisted proofs today. And in his thesis, he worked on chaos in 4 body problems. And there were pictures there that were just unbelievable. So basically, you would not believe it if there weren't a proof there. But there is a proof. And today he's actually, well, he's more a little bit wiser, older and wiser, and now he's moving back from 4 to 3 body problems, I think. And then, but then there the orbits are more complicated, maybe, yeah, because they are going to collide and eject. So, Shane, I'm happy to hear about that. Go ahead.
Thanks very much, JB, and thanks for the invitation to come talk. Yes. So, there we go. So this is based on some work with Jay, who's one of the organizers, of course, and Maciek, who gave a talk a few weeks ago. So I'll talk a little bit about about celestial mechanics, the 3-body problem, and also I'll show some pictures for the 4-body problem as well, and they're not so different with respect to what I'll talk about today. So I'll introduce those. And then I'll talk about kind of broadly about these, you know, what we kind of informally started calling the Atlas algorithm. It's kind of like some method to compute global invariant manifolds and how we use this to find connecting orbits. So this is let me actually minimize this video here so I can see everything. Okay. So this is the 3-body problem. I don't assume everyone's familiar with this, but the general idea, you can kind of read the slide here. The idea is you have 3 bodies, but one is a massless particle. So it's only being influenced by the gravitational field of the 2 massive bodies, which referred to as primaries. And so the primaries are located, when you switch to these rotating coordinates, they're located on this x-axis here. So M1 and M2 are the primaries. And we situate them in such a way that the origin is their barycenter. And when you kind of switch to the right coordinate frame, where you kind of mod out by the rotation, these primaries are now fixed in the appropriate frame of reference. And so now this becomes an autonomous system in 4 dimensions. And the massless particle is just the object that's following trajectories in this system. So we let X and Y denote its position in this configuration space, and then P and Q will denote its velocity coordinates. So we're in the restricted problem. So we assume we're restricted to a plane, and we'll have a similar setting for the 4-body problem. And so the masses of these 2 massive primaries here are also normalized to sum to 1. So the smaller one is going to be denoted by mu, and it's going to be essentially a single parameter that we have a 1-parameter really family of problems here, where the smaller mass determines the larger mass since they're normalized. What is that? Oh, okay. So the equations, if you're interested, the equations are the following. So you have, this is a Hamiltonian system. You have this potential. This is just some function on the configuration space, and you have this conserved quantity, this energy, I'll call it. Sometimes it's called the Jacobi integral. So this is conserved. The trajectories are this vector field here. So in terms of this potential, this vector field right here is what kind of is the vector field that you follow, that the massless particle follows. And so some information for us is that, you know, if I go back to that other slide, there was 5 points on there labeled L1 through L5. These are the equilibria for this system, sometimes called Lagrange points or libration points. I'll typically refer to them as equilibria, but these are all used synonymously. The 3 that are collinear along the x-axis, those guys always have center saddle stability. We're not going to talk about those. We're going to focus on L4 and L5. Let me pop back real quick. That's the top and the bottom here in this, on this triangle. These guys are symmetric with respect to the y-axis. We're going to talk about those because for some mass parameters, they can have saddle focus stability. Saddle focus meaning that they have 2-dimensional stable and 2-dimensional unstable manifolds, and those guys will be you know, a focus type. So they'll have a complex conjugate pair of stable eigenvalues and a complex conjugate pair of unstable eigenvalues. And this happens as long as the mass ratio is not too large. Ironically, it's not as widely studied because, you know, both Earth Moon and Earth Sun, which are kind of the 2 most common, you know, 3-body systems that you would look at. You would take your 2 primaries to be either Earth Moon or Earth Sun. Those both live in the regime where you don't have the saddle focus stability. But we're going to talk about the regime where you do, and that's arguably a larger region, although not as important for kind of practical applications. And so what we're interested in is going to be homoclinic or one thing we're interested in is homoclinic and heteroclinic connections between these equilibria. And so this is when the stable and unstable manifolds, they have these 2-dimensional stable and 2-dimensional unstable manifolds, and those can intersect transversely. Not in R4, which is the kind of the phase space, but they'll intersect transversely in the energy surface. So trajectories all conserve this energy, which means that the stable and unstable manifolds for, say, a single equilibrium all have to lie at the same energy. So really the manifolds themselves are 2-dimensional, but they're all living, they're kind of real ambient space should be this 3-dimensional energy manifold. And so you can have transverse intersections there. And this is the schematic. I won't put the equations up for the 4-body problem, but I'll mention some results from the 4-body problem in this talk. So this is the similar schematic here. You would have again a vector field on R4. X and Y would denote the position. P and Q would denote the velocity. And now the situation is you add an extra term to your potential for this last massive body. You would have 3 that would now be located on this equilateral triangle. With the barycenter again at the origin, and now it's a 2-parameter family. For the purposes of what I'll talk about today, not much changes as long as you're in the parameter regime where you have the center of focus stability. So all the results that I'll talk about today are either going to be ejections and collisions for the 3-body problem, or I'll talk about in general connecting orbits, heteroclinics and homoclinics for the. I could really talk just about the n-body problem, provided we're talking about, we have a saddle focus stability type. And there's a reason for focusing on that that I'll get to in a moment. So one reason to study connecting orbits, other than I like pretty pictures and connecting orbits make pretty pictures, but as well, they also kind of tell you something about how transport moves, how orbits, you know, how the global dynamics looks. If you kind of have some understanding of the connecting orbits, they somehow form a type of skeleton for the global dynamics, and you can get an understanding of how the whole system is kind of looking, how things move around, if you have an understanding of how things move around on the invariant manifolds. So here's 2 particularly interesting theorems that deal specifically with the saddle focus case. Devaney proved in the 70s that if you have a saddle focus, if you find a transverse homoclinic orbit to a saddle focus, you automatically get chaos. And then Henrard proved also in the 70s that in this setting, you have what he, I don't think he called it, I think it was called later a blue sky catastrophe, which is you have a homoclinic, which can be thought of as was often described early on as a periodic orbit as with infinite period. And so it turns out that when you have a saddle focus with a transverse homoclinic orbit, that automatically implies the existence of a family of periodic orbits that are kind of in a tube, and this tube kind of accumulates onto your homoclinic with the period growing arbitrarily large, and the stability flips infinitely often as you move along this energy. So as the energy parameterizes this tube, the period becomes arbitrarily large, and the stability flips. This is kind of indicating a period doubling, a repeated period doubling bifurcations. And so these two things are automatically forced as soon as you have this transverse homoclinic. So this is what I'll talk about. I'll talk about finding these and validating these. And so once you've done that, you've automatically kind of proved these two properties and more, right? These forcing theorems are true because these connecting orbits tell you something about the global structure of the dynamics. And so if you just kind of go look at the connecting orbits, you can just kind of look at the global dynamics. So the forcing theorems give you some information, but kind of the reason that those theorems are true is really what we're hoping to gain out of understanding the connections. I'm also going to talk about ejections and collisions. These are going to be a different type of kind of set these up as a connecting orbit of a certain type. For the moment, we have our vector field F. It's analytic away from the primaries. So as long as my X and Y coordinates are not lying at the primaries, the vector field is analytic. What happens at the primaries, though, you do have orbits that, so there are trajectories that the massless particle follows where it collides with the primaries. And in terms of the ODE, this is a finite time blow up. So the velocity coordinates go to infinity as your position converges to the location of these primaries. So we'll call it a collision if in forward time, your, capital phi here, I guess I didn't write that anywhere, is the flow for F. So if you have an orbit where in forward time, there's some fixed positive time where you land in this collision set here, which is defined to be the position of those primaries cross R2 with infinity. This would be the extended reals, because where the velocity will become infinite at that point. And then if in backward time we collide with a primary, we're going to call that an ejection. Okay, so these are also orbits that are of interest. They're not connecting orbits, but we're going to see we can put both of these kinds of orbits into the same framework where we're going to talk about an automatic way to find and validate these orbits. So we're going to talk today about two different kinds of orbits. One we'll call an ejection collision, and that's just simply an orbit that's both an ejection and a collision. So in forward time, it collides with one of the primaries, so it blows up in finite time going forward. It also blows up in finite time going backwards, where it collides with another primary, maybe the same primary. So we could talk about kind of heteroclinic or homoclinic collisions, where in forward time and backward time, both finite, it collides with two primaries. So I like to think of this as the kind of the shortest trip that you can take from, say, the Earth to the Moon, as long as you don't mind a rough landing, because you will crash into the moon with infinite velocity. So if you really got to get there fast, though, these are the orbits to follow. We want to be able to compute these and validate them. We're also going to look at the second kind of orbit that I'll look at, other than homoclinic and heteroclinic connections, is something that in forward or backward time collides with a primary, but in the other direction. I've written it here as in backward time, it's asymptotic to one of these saddle focus equilibria. So it's in backward time, as time goes to infinity, it converges to one of these equilibria, like a homoclinic or a heteroclinic would, but in forward time it collides and blows up. I'm going to call all of these objects special orbits because, as I mentioned, the framework we're going to set up is going to kind of be agnostic to whether or not I'm trying to find ejections, collisions, or homoclinics. So I'm gonna really present the problem that we have is we've got 3 different questions that we could ask when we're trying to study these sorts of orbits. So the first one is, how do we find orbits, any of these special orbits numerically? So validation aside, finding connecting orbits is often hard, it's often challenging, even numerically. And most often when you want to validate the existence of one, especially using computer-assisted proof like we do, you start with an approximation. So you have to get that numerical approximation from somewhere. And the question is, where do you get it from? It's usually taken as an assumption when you start your proof. Okay, I have an approximation, and I'm going to prove somehow that the approximation is close to a true solution. So these pictures, these are probably some of the pictures that JP was mentioning. These are from a paper in 2019 with Jay, where we did just a numerical study of homoclinic and heteroclinic connections. So these are in the 4-body problem, and I've projected in a third coordinate. So these are these are 3-dimensional projections. So we have X and Y, and then one of the velocity components is plotted in the Z direction. And so these blue globes here, these are my three primary bodies. These green and red kind of pad, these are portions of the stable and unstable manifolds for the 3 of the equilibria that are there. And these are a bunch of homoclinic, and these are a bunch of heteroclinic connections that we found numerically. So each one of those, we kind of are able to kind of globally search for these things in a systematic way, using what I'll describe that in this talk. Once you have your hands on such an orbit, then it comes up the question of, how do I validate that I actually have a heteroclinic or a homoclinic or an ejection or a collision? Any of these special orbits, how do I prove that I have these? So this is from more recent work. This is not yet published. In the 3-body problem, what we're looking at here is these red curves here are the Hills regions for the 3-body problem. If you don't know what that is, these are the curves where the velocity vector is 0. So these are 0 velocity curves. And these are 2 ejection collisions. So the large primary is over here on the right, the small primary is over here on the left. And these are orbits that in finite time, forward and backward, collide. They go from one primary body to the other. So these would be one of these very short orbits from, very short trips from the Earth to the Moon or back. So if we have a bunch of these candidates, how do we validate those? Here I'm going to say it's not. I wouldn't say that this is not a trivial question, but I will say it's well studied, and especially by the people in this seminar who have kind of Michael Plum and JB and Jean-Philippe. There's lots of people who've been validating connecting orbits and solving boundary value problems rigorously for ODEs and PDEs. So I'll talk a little bit about what becomes special, or what you have to change or add to the setup when you want to do collisions or ejections. But for homoclinics and heteroclinics, I'll just kind of say that I'm not going to say much about how that's done, because there's lots of papers that are out there and lots of approaches. I'll say a little bit about the approach that we use when I get to that point. But it is a question that comes up when we have these orbits. And then the third thing I want to talk about is if I want to study transport, then I also want to know about the non-existence of orbits. So if I have no connections, or maybe a more appropriate question is, I want to find the shortest connection, not measured in time because it would be it's asymptotic in both directions, but for say arc length, like what we've done here. This is for the 4-body problem. This was from my thesis, where we where we proved chaos in the four-body problem. We did it by applying this theorem of Devaney and finding a transverse homoclinic. And then the thing I'm going to describe, the procedure I'm going to describe, can give you information about the non-existent orbits that a boundary value solver can't really give you, because the boundary value solver can rigorously tell you, yes, you have a connection, but it can't tell you about other connections. It doesn't know about those, and so you have to do something more global, which that global scheme is how we find the orbits numerically. And the idea is we can actually make that scheme rigorous. And therefore we can rule out orbits. So when we found this orbit in the four-body problem, these were the mass parameters. If you're interested, we had to impose some velocity constraints, and a large part of the last part of this talk will be describing why we had to impose those, and how we get around that now. But okay, we don't just get a statement about the existence of this homoclinic. We were able to rule out any other homoclinics. There were no shorter homoclinics, at least not that satisfy this velocity constraint. And so I'll describe how that's done as well. JB, I don't have chat open, so just in case somebody asks a question, please stop me. Okay. Okay, so what I'm going to describe first is kind of what we informally call the Atlas algorithm, and I'll describe it in the context of stable and unstable manifolds of equilibria. It's really based on the parameterization method, and so it can be more broadly applied. But for this talk, we're interested in intersections of stable and unstable manifolds of these saddle focus equilibria. So I'll talk about how we compute these. So the kind of the starting point is this parameterization method, which is you know, widely beloved by this community. So this is due to Kepley, Deliava, and Pontic. And the idea is, I'm going to assume we're in the resonance-free case because, well, we are for the purposes of this talk. But there's a lot of work has been done on this method, and so there's a lot out there that you can kind of work. You can work around resonance conditions. So but the basic picture is you conjugate the dynamics of the local stable. It's written here as the stable, but it's equally applicable to the unstable manifold of an equilibrium. And you do this in such a way that you don't have to evaluate the flow. So it's this invariance equation here, and you're able to solve this. So this is originally proposed in these three papers in the early 2000s, and then later work largely by JB and Jay and Jean-Philippe. Developed methods for rigorously computing Taylor expansions for P. That's the goal here, is to get this conjugacy map that takes your nice dynamics down here on RD. So we have the stable manifold theorem says our dynamics are conjugate to some dynamics on this nice disk. And we actually want to compute that conjugacy, which compute an nth order Taylor expansion of this, and we'll largely be following for the purposes of this work, we use the technique that was developed by in this paper by JB, Jay, and Christian Reinhardt. So yeah, you start with a saddle focus, and now the idea is what will emerge from here is P, which is a Taylor expansion for the local stable or unstable manifold. So, and that can be made rigorous and will be when necessary. So we assume now we have this in hand. We have a local stable or unstable manifold, and we want to ultimately find intersections between these manifolds, and they're probably not going to intersect locally. So you have to grow them. And the way you do that is analytic continuation, which amounts to taking the stable and unstable manifolds. By definition, the global stable and unstable manifolds are just the forward or backward image of the local manifolds under the flow. So you have to rigorously solve an initial value problem where your initial condition isn't a point, but it's the parameterization. It's this P that we had. So it's the image of P. So you take the whole local manifold, whatever dimension it is, dimension D here, And that's going to be your initial condition. And then you solve a d+1 dimensional initial value problem where you have now another direction or another dimension that's the time dimension, where you now take the local manifold and flow forward or backward in time. So we have to rigorously solve this initial value problem with d-dimensional initial data. And we do that in the same style as the parameterization method, where we kind of have a local conjugacy. And then that's really what the flow box theorem is. When you look at it in this context, is the flow box theorem is telling you that there is a local conjugacy. So for the flow, there is this a corresponding version of capital P. And this can be solved rigorously, and as long as you take the parameterization method and you kind of somehow get away from the equilibria, now you can kind of flow and grow this whole manifold out by flowing along the boundary. So we assume we have a local manifold. We take a piece of the boundary. It's necessarily transverse to the flow. That's proved in these papers on the parameterization method. And then we compute this capital gamma here, which is the forward image of lowercase gamma. And we call this whole thing the Atlas algorithm, because it's don't have a better name for it than that. The idea is to compute a global manifold as a big atlas of local charts. So we grow it piece by piece. And so that's kind of this procedure here. We have X naught here. This initial piece out here, this kind of bowl here would be like the stable or unstable manifold that we want to grow. We have this local computation that we get from the parameterization method. And then we have this sitting there as a d+1 dimensional Taylor expansion. So we can evaluate the boundary of that, which is now a d-dimensional Taylor expansion. So of some, analytic, it's an explicit parameterization of the boundary. We can chop that up into pieces. So that here is kind of 4 different colors here where we've meshed it into 4. In this schematic, it's 1-dimensional. So these would be arcs. And then each one of these we rigorously or non-rigorously integrate forward, obtaining for each chart a new d+1 dimensional Taylor expansion, where the new dimension here is now time. So one of these patches like is pictured over here on the right. And now, so you have to do a bit of work to figure out how to do this integration, how to do this all automatically. But Taylor integrators are very kind of reliable, and they're amenable to computer-assisted proof, so we can do rigorous computations of these. And then what do you do when you want to go further? You come out here to this new patch that you have, and you evaluate the time 1 map. So you collapse onto this green boundary over here. That's a new input to your algorithm. That's a new boundary, what I would call a boundary chart. And it's d-dimensional, and now you just rigorously integrate that. And you propagate your rigorous error bounds all the way forward. So at each step, you're going to accumulate some rigorous error bound of some error bounds that you get from both wrapping from doing the finite part of the computation with interval arithmetic, and you accumulate some from the truncation error. You just propagate all that forward and keep track of things in a systematic way. And you just iterate. So the procedure kind of looks like you have a boundary, you chop it into pieces, something we call remeshing. You take each of those pieces and you add back them or integrate them, and now you have you have not just their forward image under the, but you actually have an explicit parameterization of each of these. So you actually have a bunch of charts for this manifold. So you're building an atlas out of charts. And now if you want to keep going, you evaluate the time 1 map, so that takes you to the next boundary. And then you come back here and start all over again and remesh if necessary and keep going. Okay, so this is the pictures here. So some examples of what this looks like. I guess I'll start over here on the, let me start over here on the right, I guess. So here, this is not an invariant manifold of anything. This is, again, I primarily as a lover of pretty pictures. I mean, there was a good reason to compute this, not just because it makes a pretty picture, but it does make a very pretty picture, I think. So this is, we did this in the Lorentz system for classical parameters. So it looks like the kind of like the double scroll attractor. And here it was, the idea was we took it doesn't have to be an invariant manifold for an equilibrium. The Atlas algorithms described can kind of compute forward images of any invariant sets that are transverse to the flow. So you start with a boundary here. I took the line segment between the two eyes in Lorentz, and these are, this line segment is transverse to the flow. So you then you integrate this forward, and of course what inevitably happens is this thing kind of twists. So this is now the forward image of a one-dimensional initial value problem. So the solution is a two-dimensional parameterization of this, this big chart, this atlas, and each one of these different colors is it's actually a different chart. So so you can see initially, and maybe you can't see so well, initially this red line, we took a single boundary chart, and we took a time step, so there was no remeshing required, and that's this green patch. And then of course, Lorentz is Lorentz. It starts to tear things and twist them immediately and violently. And so the remeshing algorithm kicks in and starts chopping up the boundary into pieces automatically and advecting them forward. So this, I think, was about 1,500 charts. So sitting in the computer is 1,500 two-dimensional Taylor expansions, and these are all carrying rigorous error bounds. So we have these two-dimensional Taylor expansions are stored as just as finite arrays of coefficients, Taylor coefficients, to some order, and then we carry around the errors that we've accumulated on the truncation. And so the idea is that we want to do this automatically, and that's what this algorithm I'm describing does. So we applied this now to this as the four-body problem. These are just looking down overhead in configuration space. So these are X and Y, and these three little dots here are the three massive primaries that are sitting in this equilateral triangle. And here we took the equilibrium is the L0 equilibrium at equal masses. And so we start off with kind of the local parameterization is these red and green patches. These are what we get from the parameterization method. So these are a single chart in our atlas. And once we obtain those, we turn on this algorithm that kind of grows these manifolds. They're really two-dimensional manifolds sitting in four-dimensional space. So they don't truly intersect like we're seeing here. This picture though is nice because it gives some so there's two things I like about this picture. One is it gives an impression of how quickly these atlases get very complicated, and you can't really evaluate them by eye anymore. So here already this is 5 time units forward and backward in the four-body problem. The blue here is so everywhere here the green is the stable manifold and the red is the unstable manifold, and the blue is their boundaries. And by the time we get to 5 time units, there's so many charts that we can only even see the boundaries. It's so kind of thick with charts that the boundaries have washed out all the red and green. So you could never look at this and try to say, let me go look over there for a connection. But we have an algorithm that then takes these atlases and tries to mine them systematically to find intersections. So I won't say a whole lot about that in this talk, but that algorithm is kind of necessary. So for producing those pictures that I showed earlier, where we found several hundred of these homoclinic and heteroclinic connections, you can't really do that by just growing these manifolds and then looking, by eye. You really have to have something that is global and systematic to kind of process. So here, I think the largest atlas we ended up with in this computation was 100,000 charts, which is just not going to be feasible. And in fact, we were able to get these charts, these atlases, large enough that the bottleneck in the computation time is not even computing the charts anymore. It's actually mining them for intersections. We had to do some pairwise, just take every pair of charts, one from atlas A and one from atlas B, and try to find intersections by doing Newton pairwise, because that computation just will never finish. So we had to do some things that I won't describe, but okay, they're all kind of part of this framework for automatically finding these connecting orbits. Here's again, as a lover of pretty pictures, this is the these are the stable and unstable manifolds for the same picture over here on the left for L0. And here again, I projected a third coordinate. I took one of the velocity coordinates as the z-axis, and I did these in Poivre. And the third primary is back there somewhere. And so the green is the stable manifold, the red is the unstable manifold, and the blue, these three blue curves that seem to be kind of wrapped around these manifolds. These are actually the shortest connections. So in this case, for equal masses, you actually get all of your connecting orbits come in these kind of symmetric triples. So this is, up to symmetry, this blue connecting orbit, these three connecting orbits are kind of the same up to symmetry. And Jay talked recently about work that he did with Wouter, where they are looking at what you do when you take these guys and you do continuation in the parameters and break that symmetry and try to, once you have all these homoclinics and heteroclinics, you go and look at, well, how do they kind of die? How are they destroyed? Where do they go when you do continuation? And what does that mean dynamically? So they kind of looked at the case where you do continuation in the parameters and you break the symmetry. Let's see where I'm at on time. I guess I should speed up a little bit. Maybe I'm not so bad, but speed up a little bit. When you have, again, we're just having numerically computed these connecting orbits. When you have them, you start to find some interesting things that you really didn't know existed. So we wrote this paper in 2019, where it's just a numerical study of homoclinic orbits. And what we kind of learned there, this is in the four-body problem again. And what we learned there is that these homoclinics have this kind of language, this alphabet, where you had these two kind of short homoclinics, and all the other homoclinics were kind of seemed to be arise from shadowing these two model homoclinics that we called kind of letters in our alphabet. And the longer words they would shadow, almost like almost like you would look at kind of the itinerary map as you kind of do loops around the eyes in Lorentz. And that this structure that we're seeing, this global structure, is kind of it's kind of evidence that would suggest if Devaney hadn't already proved his theorem, we might make a conjecture that theorem is, so this might be evidence that would suggest that theorem, and you could go out and look for proving it. So this is kind of looking at the evidence that theorem is true. So you have this kind of this loop right here and this loop right here. These are kind of your alphabet. And at least for the computations we did, all of those orbits that I showed in the previous slides, where I showed this kind of whole bouquet of orbits, all of those had the property that they could kind of be systematically identified as a word in this alphabet, meaning that you have, so here's a few of them over here. And what you have is that longer homoclinics will shadow one or the other of these two homoclinics, and they'll make these near misses. They'll pass very close to intersecting the stable manifold, but then they'll shoot off again following one of these two homoclinic orbits, shadow them closely, and then come back and eventually re-intersect with the stable manifold. So we found 120 some odd of these orbits, and we were able to actually classify all of them as words that shadowed these two shortest homoclinics in some kind of configuration. So here's an example of a homoclinic that we were able to find that is essentially indistinguishable from the shortest word, but it actually, you have to zoom in real close. I mean, we can see it when you mine for them pretty easily, because you automatically get the time of flight, but that connects between the local stable and the local unstable manifold. That's a finite time. And when you find these two orbits, you find one has essentially double the time of flight of the other, and so you realize these are not the same connecting orbit that you found twice. And this is, again, kind of evidence of this period doubling bifurcation. Okay, so we're able to kind of find these connecting orbits automatically. Well, we're able to prove a theorem that it kind of well, so we go and find these, and even if we do a rigorous computation on the atlases, you have to write down a theorem that you want to prove with the computer. So here is that theorem. When we're looking for these transverse homoclinics, these are some conditions that we have to check, and all of these are things that can be checked with a computer. So here, this F is constructed. We do things a little differently now, but this F is constructed by throwing away one of the coordinates, and just looking at the map that is the difference between the local stable and local unstable manifolds. And we can prove we have a zero of this by using kind of validated Newton's method. And these are the conditions that have to be checked. And then this last condition here has to be checked because well, so it goes back to this notion of it goes back to this kind of property of transversality, that we really shouldn't expect transverse connections in R4, but they're going to live in some energy surface. So we have an overdetermined problem natively, and we have to deal with that. So here we kind of unpack that by hand, and now we do things a little different that I'll get to in a moment. Okay, so you go and you prove this theorem that basically says, here's a list of conditions that we can check with a computer. So we find all these numerical connections, and then we can go and validate that these conditions hold for any of these connections, either in the charts themselves, if we compute these atlases rigorously, or in the work that I'll talk about for the remainder of this talk. We do only the numerical computation of the charts, and we do the rigorous computation, the computer-assisted proof, only on the boundary value problem. So what I'll talk about for the remainder won't deal with the case of, none of the results I have will allow us to say anything about ruling out ejections or collisions. But okay, that's work for another time. So here's the note about transversality is that if I have a saddle focus, or any equilibrium here, the property that I can talk about a transverse intersection between two-dimensional manifolds in R4, that comes from the fact that they're really living in this energy submanifold, where the energy of the stable and unstable manifolds is constant. So it's implicit function theorem. This is really a three-dimensional manifold that these pair of two-dimensional manifolds live in, and so they can and do intersect transversely. A more systematic way of solving this, and what we actually do now, is instead of throwing away this coordinate, we threw away one of our coordinates back here on F, and we had to append this gradient condition. We had to validate that. A systematic way of doing this goes back to probably the 80s or 90s. People have done this for a long time. Is to introduce this unfolding parameter, which says take your vector field F and perturb it in such a way that trajectories no longer conserve any energy. And in fact, you do this perturbation here in such a way that the energy becomes a Lyapunov function for this new vector field, meaning that the energy has to be always decreasing or increasing, I guess, if you use the opposite sign on your energy. And so then if you then go back and prove you found a connecting orbit between two manifolds that are at the same energy, then because this vector field here has to have a decreasing energy always, that implies this alpha here had to actually be 0. And what we can prove, because this is not a vector field that we want to work with in our boundary value solver, where we have to compute, we have to compute solutions to the variational equation. We don't want to append this ugly thing over here. We work instead with this kind of simpler version of an unfolding, where this is really just adding, it's adding a friction term, right? Which has the same kind of effect. It destroys the conservation of energy, and so for the same reason so we can prove that this The energy is also a Lyapunov function for this vector field. This is now linear with respect to all of our coordinates. So it's much nicer to deal with computer-assisted proof, and especially solving the variational equation. And we can prove that energy is still a Lyapunov function. And so again, for the same reason, alpha has to be 0 here if we find a solution to this boundary value problem. So I haven't explicitly written the boundary value problem. I'll do that a little bit later in the context of ejections and collisions. And this is the kind of the general framework for boundary, solving boundary value problems in homoclinics or connecting orbits not homoclinics, in Hamiltonian systems, where you have this energy. So the intersections are transverse, but not in the phase space. Okay, so the last bit I want to say about the manifolds of equilibria, here's a picture where we did this for Lorentz, is that we can validate these atlases. And this is precisely what you have to do if you want to rule out orbits. So if you want to rule out a connecting orbit, because if we have a connecting orbit and we want to validate it, we can just do a rigorous boundary value solver. You don't have to grow the whole manifold rigorously in order to prove rigorously that you have a connecting orbit. So you could do, and what we do for the remainder of the results I'll present, is numerically compute all the atlases, numerically search for, globally for connecting orbits, these special orbits. And then once you have them, then do a rigorous boundary value solver. So that's what we've done, but that's not required. We actually can, and when we started doing this, we were rigorously computing these atlases. And then once you find the intersections, you're done. You don't have to do any boundary value solver on the back end. Of course, this is a lot more computation. But what you gain there by having the access to rigorous parameterizations of these global manifolds is that's the only real way that I know of to rule out connecting orbits. Where if you have two atlases and you can not only search charts for intersections, you can also prove rigorously that you have no intersections, which means you can't have connecting orbits. And this is how we proved, for example, this theorem about having the shortest connecting orbit in this previous slide that I had. We rigorously computed these manifolds. So here's a picture I like to show because it's pretty, and it just shows how complicated Lorentz is. Even for something so well studied. Back here is kind of this double scroll is back in there somewhere. This is the two-dimensional stable manifold at the origin, and this thing kind of spirals out very, very quickly, and then the slow manifold, the slow stable part, kind of starts twisting and folding back on itself, and you can see lots and lots of layers here. And this computation was done rigorously doing this atlas algorithm, where we just take this integration that we have to do on the boundary, and we just have to make that a rigorous integration. So a rigorous Taylor integrator. I'm going to go real briefly over how that's done, mainly because in this crowd, in this community, I think the kind of the standard is to write down this Newton-like operator. So you look for a contraction mapping, and your contraction that you try to form is something where you have a zero finding problem, and you define T to be your zero finding problem F minus an approximate inverse of the derivative times f of x at your approximation. And in fact, this picture here, that was actually done doing precisely this method. And the difficulty there is when you want to validate an atlas with thousands of charts, the approximate inverse is some big matrix, and you've got a bunch of interval computations with accumulated error, and you're trying to do validated computations of that bound the norm of this matrix, and that's computationally complicated. It's computationally difficult, but it works very well. However, the computations that we tend to do now are based on a method that Hans and Gianni wrote about in I guess 2015, I think, and we've kind of taken their idea. Their idea is that you can try to force the Newton-like operator to be a contraction. It turns out, though, that coefficients of this analytic expansion decay geometrically. The map itself that just maps onto the coefficients is a contraction, And so we deal with, this is what we kind of call the matrix-free approach, which is specific to Taylor now. We can no longer do expansions in time with, say, Chebyshev, which is nice because it has these nice convergence properties. So you can do these boundary value solvers, or even these initial value problems. JB has a paper with Christian on doing initial value problems with as Chebyshev expansions, and JB has a paper with Rai on how to automatically do the domain decomposition for the Chebyshev nodes. That kind of is not amenable to this approach. So you give up something by working with this matrix-free approach. So, but just for since not everybody here has maybe seen this, the idea is very similar to what we're used to. We have the flow. It's expanded into as a a series in psi here is just whatever our basis functions are, whether Taylor, Fourier, or Chebyshev, and we transform this into a fixed point problem on the space of sequences. So we only really care about the A's, and these are d+1 infinite, and we pick a nice function space to work in, and so the main difference comes, so we break this space up into the truncation part and the tail, or the remainder. And the main difference in the notation that we use nowadays, the map that Hans and Gianni wrote down, I would express now in this form here. So it's not, you'll notice it's not a Newton-like operator. It's just this time rescaling, and then you project onto the tail part, and this I here is something that it's essentially the integration operator on sequences, so on Taylor series. Okay, so what it does is it takes the m plus first term and it divides by m+1. Okay, and so you can kind of write it down in this higher level functional analytic setting. And then their approach is to notice that T is actually typically already a contraction. And in fact, you can prove that you can always choose tau so that T is a contraction. So this will always work. There's no matrix here to invert numerically. But again, you pay a price for that, but you gain a lot computationally. So you can prove then, so we can take their kind of approach and put it into the radii polynomial setup, which is we want to kind of flip this contraction mapping theorem around, and so you can appropriately define the y0 that we all love and the z bounds, which are these three, and you can define the radii polynomial that we're used to working with, and you have the same kind of theorem. When this guy is negative, you automatically have a unique fixed point for T, and unique fixed points of T are rather fixed points of T are kind of in correspondence with solutions to the differential equation. Okay, and so I've got 5 minutes left. That's not much. So I maybe go 5 minutes over or so, but we started a little bit late, so hopefully you'll forgive me. So the last part of the talk, I want to talk about how do we do atlases for ejections and collisions. So in the previous part, we started with the parameterization method. So we had a local manifold for an equilibrium, and we just don't have that for collisions. And by near misses, what I mean is I didn't actually say it, I think. The other thing I like two things about this picture. The other thing I like is these holes around the primaries. These guys, when we did this computation, and the reason for that velocity constraint that we had on this shortest connection is that, well, as you get close to these primaries, the integrator becomes extremely stiff. So these holes are here because every time the manifolds would get close to the primaries, they would basically be trying to blow up, and you have to stop integrating or else you'll just hang there. You'll just integrate forever. So you have to kind of cut that piece away. So that's the reason that these holes are here. But these manifolds actually do intersect the primaries. In fact, that's what a collision is. If I have an equilibrium collision, that's an intersection between the unstable manifold of one of these equilibria and this primary. And so So we have these kind of problems. We can't compute collisions and ejections by just applying the algorithm I just described. And when we compute them, even using the algorithm I just described, what I would call a near miss, meaning the manifold gets close to one of the primaries, it turns out they can get arbitrarily close, which means the integrator gets very stiff. So you have to stop integrating, and that translates to this constraint where I have to bound the velocity, and I can only make statements about the shortest homoclinics if I introduce a velocity constraint, because I had to kind of cut away part of the manifold and stop integrating it. And so I can't make a statement globally about that being say the shortest homoclinic. So even when the manifolds get close to the primaries, this is problematic. And that's what that picture illustrates. So I want to know, how do I, so the idea here is to use this classical Levi-Civita regularization, which is a way of kind of desingularizing these vector fields near the primaries. So the setup goes, we have two primaries, so there's going to be two different kind of regularization maps. So we're going to have three sets of coordinates that we work in. We're going to have these, what I call the standard coordinates. So now I'll denote F always by an F naught, and the U, I'll denote that by U naught. This is the standard coordinates where we did all the computations that we've seen so far. And I'll use kind of capital X naught to denote the copy of R4 where those guys live. So all three of these coordinates will be copies of R4, but they're really different coordinates. And so the Levi-Civita regularization says roughly there's a semi-conjugacy. You have this mapping. You fix an energy, and there's a mapping that takes your standard vector field to, vector fields I'll denote by F1 or F2, and the property that F1 and F2 have is that they're desingularized at the mass M1 or M2. So we do this coordinate change, and then we have a corresponding vector field. So the idea is, what we're going to do is when our manifold gets close to a primary, we're going to do a coordinate transformation. We're going to now have a different vector field. We're going to follow orbits over there. We're going to compute the manifold over there. Over there, it does not get stiff near the primary. And we're going to follow it over there and then come back as needed. So we want to do all this in an automatic way. And it's worth pointing out, the zero energy level set is the only set that's dynamically meaningful, because you actually have a family of these. See here as a parameter. And so you have a family of these guys. And so your new vector field only has a dynamical relevance to the original when you look at the C equals zero energy. So just to maps look like, here's the coordinate map that takes you from standard coordinates over to the coordinates where the new vector field is no longer singular at the large primary. So here's the computations that you do. I won't go into detail about where this is derived. Again, this is kind of classical. I didn't invent this. I'll say that the main complication that arises for us is that X naught and Y naught here, these aren't points like they are for an orbit. For us, they're going to be manifolds, which means that X naught you should think of as a d-dimensional Taylor series. Y naught is a d-dimensional Taylor series. So I have to be able to compute the real part of the square root of X naught plus I Y naught minus mu. And so there's some work that has to be done there, especially to do that automatically. That took quite a bit of work. And then going back, so I have to essentially be able to compute square roots of Taylor series, which of course we know how to do. But it's still quite a bit of work. I also have to be able to divide by these variables. So again, this thing in the denominator over here on P naught or on Q naught, this is a Taylor series. In the denominator, I have to be able to divide. And so we have algorithms that kind of apply automatic differentiation to turn all this into a differential equation that we can solve, and we can do that rigorously. But this is quite a bit of work. But once you've kind of worked that out and done so in an automatic way, we can take manifolds and just kind of what I call hot swapping. You just swap around to whatever coordinates you want, and we can even propagate the errors. So in the manifolds I'm talking about, we haven't done this rigorously, but the kind of the limitation would be computing rigorous square roots of Taylor series or rigorous inverses of Taylor series, and we can do that. I won't go into detail about how, but this can be turned into another d-dimensional initial value problem that we know how to rigorously integrate. And the other thing to focus on is that the collisions now, so the collision set C, what I had in the other slide, what does that look like after I've done this coordinate transformation? It turns out this is actually just parameterized by this circle. So over here in the regularized coordinates, I have this circle. Here's the formula for it. And what I want to focus on is that that's a nice manifold in the regularized coordinates, and it's flow transverse. So this is where I'm going to get my hands on a local, you know, the collision version of the local manifold that I need to start doing analytic continuation. So the kind of revisions that we need to make for the Atlas algorithm for the Equilibria is, well, we need to kind of notice and implement it in such a way that it applies to arbitrary flow transverse manifolds of initial conditions. That I have a picture of that that Jay made on the next slide. We have it, you know, kind of implemented in such a way that we can automatically do this hot swapping to avoid dealing with singular vector fields. So anytime we get close to a primary, we switch over to a nicer set of coordinates. We compute the manifold over there. When it starts wandering back into the region where, you know, that vector field itself has kind of singular points, when it starts wandering away from where the, you know, the nice region is, we switch back, and we do all this automatically, and we build up these atlases where now our atlases are charts that are in 3 different sets of coordinates, but we can keep track of the mappings between them and time. Okay, I've already mentioned that the initial data are sequences in L1, so that requires rigorously solving differential algebraic equations. And then keeping time. I haven't said how Levi-Civita, how the time rescaling works. So I kind of didn't want to put any more formulas on the slide. The short answer is it's kind of it's an integral. But we can compute it, and we can compute it for L1 sequences. So that's all we need. And so for collision manifolds, we kind of had this schematic picture. Yes. Yes.
You work towards a conclusion.
Yes, sorry. I have, I think, 3 more slides, maybe 2 more slides. Yes, sorry. Okay, so the picture is I've got these, if I want, for example, an ejection collision, I've got a circle that parameterizes my initial conditions for one primary, another circle over here, M1. This is the collisions for the other primary, and this kind of schematic of the energy level set where these guys live. So I compute the regularization maps all at the same energy, and then, well, we can kind of glue these things together, and we do this for the boundary value solver, which we need to carry out rigorously. We glue these things together, and you prove that you can do that in such a way that you build a big zero finding problem, and you do that in such a way that the solutions actually correspond to collisions. So we grow the manifolds by swapping back and forth, and our boundary value solver also has to deal with that. So I'll say very briefly then how that works. The boundary value solver, I haven't talked about this kind of the usual way people solve these. You make a zero finding problem, these multiple shootings segments, and here we have to do one of those for every regularization type. So as we move around between these coordinate systems, we have what I'm calling strands. So a strand is a single kind of multiple shooting problem that only deals with a single regularization type. And what you do is you take the classical multiple shooting zero finding problem, and you append to the end of it a coordinate transform that is mapping into the next set of coordinates. And so this is a picture. If I go back to this picture, that's what these colors are along the orbits here. So this boundary value problem would have 3 strands. And so what you would, a multiple shooting problem for the green strand, and the last coordinate in your map, in your zero finding problem, is the one that checks that the mapping of the terminal point on this green strand under the conjugacy map takes you to the correct point on the blue strand. And you use these to kind of glue together these three multiple shooting problems. And so these all get concatenated into a big zero finding problem. Okay, so now that zero finding problem, again, we use kind of typical methods for validating that. Okay, so the rest is pictures that I'll show very briefly. So here is numerical computations of the 9 shortest homoclinics for L4. It's a conjecture because I haven't computed rigorously the global manifolds. Again, I'm only numerically computing these. But I claim that they're the shortest because here I've done the regularization. So there's no need to cut those holes out around the primaries. So orbits that pass arbitrarily close to the primaries are okay. I can still integrate those. Here are some ejection collisions. Again, these are all numerical. These are not validated yet. So these are things that leave the first primary here. They wander around and then they collide again in forward time. So there's like 81 of these. M1 to M2, these are ejection collisions that leave the large primary and collide with the small primary. And now here's the validation of one of these guys. So each of these other kind of numerical conjectures can be validated using this this boundary value solver. And here's one. This literally came last night. Jay sent me this. So this is recent work in the sense that this is 12 hours old. Here, this is a rigorous proof of a equilibrium collision. So this is an orbit that leaves the L4 equilibrium and in finite time collides with the large primary over here. So this is now the rigorous error bound on the solution to this boundary value solver. And that's it. Okay, thank you for your attention. I'm sorry for going a few minutes over.
Thank you, Shane, for a very nice talk. Very nice picture at the end, I must say. Are there any questions for Shane? Let me start, otherwise. So these ejection collision things, they happen in finite time, right? From ejection all the way up to collision.
Correct.
So in principle, you could try to find the shortest ejection collision, right? That's at least that is now a nicely well-defined problem, and all these other shortest connections, they are in some arbitrary measure somehow shortest, right? Whereas this one would really be in real time. So is there any hope to try to do that problem?
Yeah, that's completely. So that's what I was saying a little bit about we need to then do what we're doing right now is we take these two circles and we build these kind of atlases of these circles of initial conditions. We're doing all that non-rigorously, and then we rigorously solve the boundary value problem once we've found a numerical connection. We would need to then, to do what you're describing, we would need to rule out ejection collisions, which would mean going back and rigorously integrating those manifolds. So we would need to do those atlases rigorously. That's completely doable in the framework of what we have and what we're able to do, but we haven't done that yet.
Okay, thanks. Other people with questions?
Yeah, Shane, I have a question. So my question is about this this phenomenon that you have observed, this per doubling bifurcation. How can you explain that this occurs? Because typically it should not occur.
Could you be more specific?
Well, in the sense that, okay, I mean, if you have a typical homoclinic orbit with, let's say, a bound of, a property that you can verify, including the one you gave in your theorem, that you have some form of transversality and whatnot. In general, such orbit do not necessarily return to itself unless it is already some sort of degenerate in some sense.
Well, it's Hamiltonian, so it is degenerate in some sense. But that's not what you meant?
Yeah, I'm not sure. Okay, maybe you're right. Okay. Okay, maybe.
So it definitely appears that as soon as you have two of these things, you have infinitely many, not just periodic orbits shadowing them, but homoclinic orbits, other connecting orbits shadowing.
Oh, is that what you were asking, Vincent, about the nearby homoclinics?
Yes, right.
Yeah, so we have observed that these homoclinics in particular appear to enter and leave the stable and unstable manifolds on very, very narrow regions of the boundary. And as far as I know, so we don't have an explanation for that. And as far as I know, this was never observed before this paper that we had, because, you know, we kind of have I think that this is the first time anybody had this many connecting orbits all sitting in one place and could kind of look, okay, where do they all leave and enter this local manifold? And it turns out they all leave and enter in very, very narrow strips of the boundary. But I don't have a theorem that says that has to be true, and I don't even understand why that's true.
All right, well, fair enough.
Other questions? Okay, well, if not, then thanks again, Shane, a lot for your very nice talk. It's very nice, indeed, again, very nice pictures. I'm not sure Jason really agrees that this is linear algebra done right, but seems to think.
Yeah, this is always my favorite picture.
I don't know.
Yeah, that was the paternity test. That's how I knew it was my kid.
Okay.
Just started reading it.
But thank you very much. And thank you all participants for attending again. And I hope to see you back next week.